It took one look, I know you stare at me the same. It took one look, but you play me like a game. I can see. It took one look, I know you stare at me the same. It took one look, but you play me like a game.
Out on Alright, what's up everybody? Happy Sunday. How's it going? Happy Sunday, happy Sunday, happy day. It's been a good day so far. I've had a fantastic day. How's everybody doing? Sending a text. Oh, no hot water. Ugh. Ugh, that's no fun. Favorite coffee shop is closed. My favorite coffee shop is right here. Alright. I have to fill my tires with more air tonight. That's on my to-do list. Still haven't done that yet. Since I've been down here, it's getting cold. It's getting really, really cold. And my tires are currently pumped for like summer weather, and I still haven't changed that yet. I really need to hop on that. Yeah, no hot water is no good. Well, cold. I don't mean like cold. Ugh. Well, there you go, Demonati. You have a place to call your own, and that's the key. Oh, come on. Thanks, Case. Oh, there we go. Finally popped out. Okay. No, Thread, that's not how that works. No, Demonata. No, that's not how it works. That's no bueno. Oh boy. Oh boy, this is gonna be a fun one. This is gonna be fun. Oh boy. Oh yeah. Haha, plenty of cool things here. There's one equation that I need that I'm gonna leave open, so hold on a second. Okay. It's open. Got it. Ah. Rocket League style. Have to make your brain boil? Oh jeez. That doesn't sound good. I'll try to help to the best of my ability. For you to be able to do that, of course. I need to work out today. I need to work out for like 6 hours. I haven't worked out enough because you guys are eating up all my time. It's not your fault. It's my fault. I'm just kidding. I'm not putting the blame all on you. I'll take some of the blame, but you're eating up all my time. 3, 2, 1, Tylenol, IBU, leave. Nice. Hey, Novus, what's up, man? How are you? Happy Sunday, dude. Not my Tylenol. I've got my coffee ready. I might have to whip out the aspirin if this derivation gets too difficult. I don't think it will. I think I'm actually able to do this now since I've done it so many times without notes. So we'll see what happens. I think I'm able to do it without notes though. I know, you guys, you tell me to take a break. I know, Demonata. Mank, that is totally not a good idea. I think there's a Kroger 5 minutes away from where I live, and I think I think there's a tire station, but I've quite literally never filled my tires before, so I don't know what the procedure is. Novus, sitting at the airport. Where are you going again? I remember you told me. But now I'm blanking, man. Because wait, did you end up telling me? I remember you saying that you weren't able to come to the stream today. But I don't know if you told me where you were going. You could have. I could have forgotten. My memory's been pretty poor recently on the weekends for some reason. Probably because I'm sitting in front of the computer screen all day. Alright. Let's go like this. Used to be a KSP stream? No, Benin. It never was a KSP stream. It was always about science and engineering. I just used KSP to reel you guys in so I could teach you about the real things. That's right, Novus. You're going down to math. Nice. Oh boy, Divinata. No, I use KSP as bait for you guys. And once you guys are reeled in with the KSP content, I can start going over real content with you guys. That's the key. And before you know it, you're going to actually start enjoying this stuff. Alright, so anyway, another general update. So let me write this down. I'm going to do something really cool. Alright, I'm going to do something really, really cool. Next Wednesday. Wow, that was not an N. Anyway, next Wednesday, which is what day? I'm not wearing my watch. Demonata, that's right. You were here for Minecraft. I haven't played Minecraft in a while. I totally forgot about that. What's up, Kelly Johnson? Hey! How's it going, Sentinel? Welcome, man. Welcome. November 8th. Got it. What's up, Kelly? Yeah, Demonata, that's right. I forgot you were a, Minecraft, persona. I totally forgot about that. Next Wednesday, I am releasing... I'm doing it right. I'm releasing a worksheet English. Worksheet number 1. You bet. As I said in the beginning of this, I will be releasing worksheets. They're not required, okay? Oh, shut up, Demonata. You still love it. You still love hanging out. Demonata, don't leave. I need you here. I need you here. But, yeah, I'm going to be releasing a worksheet on Wednesday. Worksheet number 1. Now, your reward for doing this worksheet... Nah, I'm not going to write that down. Sounds good, Novus. I'll probably be streaming a little bit later, man. Good luck, man. Good luck with the flight. Guys, the reward... I'm going to turn the music down so you guys can hear me. The reward for you doing this worksheet is that I will spend time extensively going over your worksheet and mistakes, write personalized corrections for them, and then return them to you and talk to you about what you did wrong. Again, the whole point is that I want you guys to understand this, okay? That's all. I want you to understand this stuff. So, if you go through and if you do this worksheet, your reward for doing this worksheet is that you get more personal time with me. And I will tell you exactly what you're doing. But yeah, I do, Demonata. Like, yes, I do. Like, funny joke, but I will have time, man. I will have time. And I will help you correct. I will help you fix the mistakes. So that is your awesome reward for doing this. I will go through the problems. I will write personalized corrections. And I will tell you what you're doing wrong. Okay? There you go, Sentinel. Get them all wrong. Doesn't matter. You can get them all wrong if you want to. It's really not a problem. Not a problem at all. Anyway, that is the reward. Okay? 24-hour stream confirmed. No, it's not going to take that long. Orbital elements. Cool. Orbital elements. Alright, so, we live in somewhat approximately a Cartesian system, right? So that's 2 points. That's 2 points right there. There you go. No, Kelly. No. That's not the plan. They're orbital elements. All right, we live in a Cartesian system. We live in... Cool. We live in an approximate Cartesian system. So, if we want to define our mechanical state at any point, so to define our mechanical state, we need what? We need, and I'm looking for a number, and I want you guys to answer this. We need blank components. How many individual values do we need? Nice, Steven Otta. To define our mechanical state in a Cartesian system, how many different components do we need? Kelly Johnson, incorrect. Minus 1,000,000 space coins for you. How many different components do we need to fully define ourselves? There it is, Oyashiro. We need 6 components. We need 6 components. Alright, we need 6 components. Oh, hold on a second. I'm on text duty here, so sorry about that. Over 9,000! No, not over 9,000. You need 6 different components, okay? Now, if we are in a Cartesian system, it's relatively simple, okay? I can totally take those away. No, I'm just kidding. Don't take any away. I hate taking away space coins. I don't like that. Anyway, if you're in a Cartesian system... Oh, different color. If we're in a Cartesian system... it's pretty obvious, right? So this is, if this is I, J, and K, which are just, they're the same exact components of, you know, X, Y, and G, right? A link from EJ's stream 2 hours ago? Was EJ streaming 2 hours ago? I didn't even see he was online. So anyway, if this is your R vector, you're right. Your R vector is made up of 3 components. It's made up of Rx, oh, that's not Rx. That's Ry, Rx, and Rz, right? That's 3 right there. Did I say XYG? Did I say XYG? Oh, geez, sorry, XYZ. Sorry. And then, right, your object will also have a velocity to it. And that velocity has also got 3 different components to it, right? V, Y, Vx, and Vz. Okay, so those are our 4 components, okay? Oh, cool, Yoshiro. I did not mean to say G. Sorry about that. It's really bad. IJK, XYZ, yeah, it doesn't, it's just any 3 set of letters. It doesn't matter. It really doesn't matter. The G coordinate? No, don't worry about the G coordinate. There's plenty of other coordinates that we're gonna get to, though, so... retain that fear. Anyway, here's the thing, right? I'm thinking about gravity. Right, so here's the problem with this system right here. We have a Cartesian system, right? Rx is actually not a constant, right? Rx is a function of time. So is, you know, Ry, it's also a function of time. Rz is also a function of time. And then we can write the velocity in the same form. So Vx is also a function of time. Vy is a function of time. Vz is equal to Vz, a function of time. They're all functions of time. Yeah, I guess I was thinking about gravity. The gravity component. Nice, dude. But yeah, so all 4 of these... No, not that Threnan. See, this is why I have to go back and remake these videos, because all of you guys just fool around. I should throw you on detention. I should throw you on detention. That's what I should do. And I'm obviously joking. I really don't care what you say during the stream. Well, I do. Wow, that came out wrong. Wouldn't there be 7 components? I'm assuming that you're in Cartesian space, so time is the independent variable here. If you were not in a Cartesian space, then yeah, there would be 7, because you'd have time dilation and whatnot. So yeah, that's... Ooh, we should like make a way to add people to a list of detention people. Anyway, I said that earlier. You're assuming you're in Cartesian space. But yeah, technically, time is... Well, no, that's not true. Time, these are your dependent variables. They're dependent on things, right? Time is your independent variable. So really, the state is just 6 dependent variables. That's what it is. Your time is just your one independent component that you can, move the slider along. Here's the thing. These are all dependent on time, okay? All dependent on time. All dependent on time. All dependent on time. And obviously, it's kind of hard to follow, right? I mean, like, you see this, and there's nothing physically like that catches your eye, right? You see this, and you're like, all right, I've got 3 position vectors, 3 velocity vectors, but it's not really in orbit, right? So in the two-body problem, it makes it hard to visualize the orbit. Makes it hard to visualize the orbit, right? There's really no way to tell. Oh, I'm fine with it. I'm fine with it again. Doesn't matter. But anyway, in two-body problem, you can't really visualize your orbit from this information. It's really just nothing there. So let's do a few things here. Objective, right? Objective. Two things. Give 6 other components. 6 other components that do have an easy visual component, right? We want 6 components, because again, we need 6. We need 6. That's a requirement. 6 are required to define your position in Cartesian space. We need 6 components that do have a rather easy visual to them, right? And the other thing we want to do is we want to remove time dependencies from these. Remove time dependencies from these. So let's try to turn some of these in the two-body problem into constants for a specific two-body orbit. And again, assumption. This is the two-body problem. Two-body problem. Okay, let's do some math. Who's excited? All right, so anyway, let's take a look at what we can set up here and what we can do, right? So, I'm going to have a visual here going into my head. Yeah, that wasn't good. Let's go like this instead. Yeah, I like that a lot better. So, let's draw an orbit. That's first, right? Like what we define as being an orbit. And we're going to draw it component by component here. Anyway, so we've got... that was crap. That was a little better. So we've got a body that we're rotating around, right? Two-body problem marriage. Yeah, it's the two-body problem, not the two-body solution. So we've got this connection point, right? That you can sort of imagine the IJ and K axes are, coming out of. This is the J axis, and this is the K axis. Alright, and then, right, we've got something that's orbiting. So let's do that, right? So we've got, let's say this is your object, right, in 3D space. And this is your R vector. And then you've got a velocity in this direction. Oh, that was crap. How do I want to display this? Sure, we'll go like that. We'll make it a really nasty orbit. No, I don't want to do that. I'm trying to think of a way to do this here. Alright, oh, I've got an idea. So, for velocity, first things first, let's draw this, right? All the different components. So this is your position vector, right? And if you guys have trouble visualizing this, let me know, and I'll try to fix it for you, okay? Anyway, our velocity vector, what you can imagine a velocity vector is doing is sort of going into the page, okay? So our velocity vector is really pointing in this direction, down here. I really hope you guys can understand what's going on here. Alright, do you guys understand that your velocity is sort of going into the page? Going into the page. Okay, we got that. Next up, so we've got 6 components right here, right? So we've got the vector is equal to the vector components Rx, Ry, and Rz, and then the velocity vector is equal to Vx, Vy, and Vz. Okay. Opposite of I. Yes, opposite of I. That's, yeah. Opposite of the I unit vector. Opposite of the I unit vector. That's exactly what's happening. So as you can imagine, right, the orbit, eventually, once we get this all set up, will look like this, right? The orbit, as you can imagine, if you've got a velocity moving in this direction, if you got your position in this direction, your orbit's probably going to look something like this, right? Right, so, and what we're trying to do is derive all of the parameters for that, which is relatively straightforward. Don't worry. No fret. No need to fret. But this is the orbit that we're trying to come up with. And here's how we're going to do that. So we've got these two, alright? We're going to define a new vector. Oh, crap. Come on. And this vector is going to, it's called the angular momentum vector, okay? So define h, your angular momentum vector, equals angular momentum. Okay, I don't know if you guys are familiar with what h is. How would you get from... I'm curious if you guys know, or if I should just say it. Alright, I'll just say it. I think that's a little bit too complex. Anyway, the h is equal to, when you have your state vectors, the cross product of the r vector and your velocity vector. Okay, that's what h stands for. So what you can imagine is that you've got your radius vector right here. Okay, and you've got your velocity vector, which I didn't label. Silly me. Okay, what you're doing, right, is you're taking R and you're crossing it into V, so you can almost imagine that if you take your right hand, you throw your fingers along the R vector, and then you curl around to the direction of the velocity vector. Whatever direction your thumb is pointing, that's the cross product. There's so many different ways to do that, but that's just the way that I like looking at it. So that's what we're going to do. Right hand roll, exactly, the right hand roll. So that's what the angular momentum vector is. Whoa. So let's draw that, right? So if you've got R and if you've got V, you're going to have H coming out just like that. Just going to draw H here. Okay. Boom. We've got H. Let's see. Sorry, I'm thinking about what I want to do here. Okay, yeah. So we've got H, all right, and H is a vector. H also has 3 components, right? And again, H is kind of popping up the top of the body you're orbiting, like right about there, I'd say. So that's where H is popping out. It's popping out on the other side. It's the cross product of R and V. So we've got our angular momentum defined now. Let's continue on. First thing we're gonna define one parameter, and this parameter is going to be this angle right here. Okay, this angle right here. It's the angle in between your angular momentum vector and the z-axis of your coordinate frame. Okay, so this parameter is then equal to h. Well, would you guys know what it is? It's equal to the arc cosine. It's arc cosine. Well, I'm gonna do inverse cosine, just a little bit easier. Inverse cosine of h dot k over the magnitude of the h vector. Okay. So here's what you guys can imagine, right? This is how you calculate that angle right there. And how I got there is just from the rule of dot products, right? This comes from, well, let me start from that. Maybe it'd be a little bit easier for me to start from that, right? So to get an angle in between any two vectors, to find angle between two vectors, what you would do is this. Let's say you have vectors A and B. Then, right, you would know the cosine of the angle between them, A to B, is equal to the A vector dotted by the B vector over the magnitude of A multiplied by the magnitude of B. Okay? That's how you find that angle. So let's calculate that angle in this sense, right? So we've got cosine. We need a good color. So we've got cosine of some parameter, right? Is equal to h dot k over what? The magnitude, and you'll see that I actually just did this. Instead of multiplying by both, I'm only multiplying by the h. Why am I allowed to do that? Why do I not have to? And this is a unit vector. This is not just any vector. This is a unit vector, so I'm going to throw a hat on top of it. Why am I allowed to do this? Why do I not need this as well? Why do I not need the magnitude of the k hat? Why do I not need that? There you go. K hat is 1. Yeah, Lizard Commander. A little bit more specific. Yeah, the magnitude of any unit vector is equal to 1. Exactly. So, this would just be a value of 1, so we don't need that right there, right? So anyway, we've got this then, right? We've got this really simple equation, and we can transform this into... what? Actually, I'll leave everything on this side for now. No, it's kind of weird because my head is... kind of going into the page here. Anyway, so we've got this then. Excuse me. Sorry. Still trying to work out the kinks of this new tablet. So we've got this then, right? So we've got some parameter is equal to the cosine, the inverse cosine of this. H dot k, right? And k, explanation seems more logical, yeah. K is really just this. K is really just this. 0, 0, 1. Because that's what the vector is, right? It's just a unit vector in the z direction, and this x, y, and z. Over the magnitude of h, so just h, right? And we can simplify this even further. Cosine of -1. So let's take a look at the h vector, right? hx, hy, hz, dot product of 0, 0, 1. All over the magnitude of h. What will the result of this dot product be right here in between hx, hy, h, and z, hx, hy, hg, and the unit vector in the z direction? What will be the dot product of that? And it's pretty straightforward, so hopefully you guys can get that. Anyway, so the result is this. is equal to cosine -1 of the solution over the magnitude of h. What would be a solution? Yep, hz. You got it. hz over h. So that simplifies things a little bit, right? So you look at your... So here's what you would do. You calculate your h vector. You get the magnitude of your h vector. Then you look at the z component of your h vector. And once you have that information, you can find this right here. Now let's check this out, all right? Let's check this out. Let's check out what this is, right? So all we're comparing then, right, is we've got a total magnitude here, but then we've also got a z component, which seems to be drifting offwards to the side, interestingly enough. So we've got a z component, right? So this is hz. Check this out. What if, right? So again, this defines our orbit right here. I'm gonna go like this. I'm gonna continue to draw this diagram over and over again. I think that's the best way to go about it, instead of continuing to reference that one. So we've got a body, and then we've got an orbit, right, like this, and we've got an h vector. Then our h vector, if you're taking, again, this is r and this is v coming out here. So the cross product of those is really just your orbital plane. So this is my h vector, and then this is my z, okay? This is my z. And obviously, this angle that we just solved for is this right here, right? This is that component that we're trying to solve for, okay? Now, let's take a look at a different orbit. This is the first parameter that we need. Let's take a look at another orbit, all right? And this one, the orbit's gonna be a little bit different, right? Let's take a look at an orbit that looks like this with respect to our, whoa, okay. In this case, right, if we look at our angular momentum vector, our angular momentum vector looks like this, which means the angle in between these two values is 0. What do you think is this parameter right here? What do you typically call this parameter then? The angle in between your angular momentum vector and your z-axis. Check this out. If we look at an orbit that looks like this, there's nothing here. But if we look at an orbit that looks like this, there is an angle to it. What is the name of this orbital parameter? What is the name of this orbital element? I'm just going to draw h vector here. I really hope that some of you guys know this. I mean, all the KSP players out there should get this right away. What is the name of this what is the name of this element? There it is. Thank you, Mank. No, this angle is inclination. Look. This orbit, the dot product in between, well, not the dot, the angle in between your angular momentum vector and your z-axis is 0. Look at that. There's nothing there. But look at this. Look at this other strange orbit that is different for some reason. Why is it different? It's different because it has orbital inclination. It's different because there is a value in between there is an angle in between your angular momentum vector and your z-axis vector. That's what inclination is. So let's draw that in. I'm gonna put an I, right, for inclination. We've got inclination down. So we've solved for inclination. That's what inclination is right there. And let's put an I right there, right? Look at that. We've got inclination. Pretty straightforward, right? Okay. Inclination. There it is. I guess, Kelly. I guess. Sure, Kelly. Anything for you, man. You can think it's that way. Sure. But that's what inclination is. It's actually just the dot product in between your angular momentum vector and the z-axis of your system. That's what inclination is. This is inclination right here. So, we've got 1 of 6 down. Congratulations. That's how we've calculated 1. But we're not done yet. Okay. We are absolutely not done yet. The other thing we're going to do is the following. Yeah, I guess we can start with this. Okay. You guys also know what eccentricity is, I'm assuming, right? You've heard of eccentricity before? What is eccentricity? Could you guys describe eccentricity for me? While I get set up for this next component here. Inclination. Yeah, there you go. Whatever you want it to be, it can be that. I really don't care. What is inclination, right? So let's say this is the body you're orbiting. This is your spacecraft with a position vector that looks like this and a velocity vector that looks like this, right? Yeah, it's basically defining how elliptic your orbit is, right? Yes, how eccentric your orbit is. That's exactly what it is. So this is an ellipse, right? Which means that it has eccentricity, right? Fun fact, eccentricity is not just a magnitude value. It's actually a vector, okay? And it's a vector that points in the direction of your periapsis vector. Whoa. So this is your eccentricity right here. That's your eccentricity vector, okay? Looks like a potato. You look like a potato. But this is your eccentricity vector. Now, taking the magnitude of eccentricity will give you information about like what eccentricity is, right? But it's actually a vector. It's not just a magnitude value. I joke, Kelly. I joke. But it's a vector to start. It's a vector first and foremost, okay? But again, what we define as the second orbital element is a scalar. So we can just take the magnitude of this eccentricity vector, right? Anyway, there's two ways that I can do this, but I'm going to do it the weird way first. I will, at a later time, go over the derivation for this. For now, this is an assumption. This is just one of those assumptions. I'm not going to go over the derivation of the eccentricity vector. Just trust me, this is the eccentricity vector, okay? Your eccentricity vector is equal to the following. B squared over mu minus mu, better mu, minus 1 over r multiplied by the radius vector. Okay, so it's a scalar multiplied by the radius vector minus your radius vector dotted with your velocity vector over mu in the direction of your velocity vector, okay? So this right here is scalar, and so is this. However, these two right here are vectors. Right? So we're essentially adding two vectors together. That's what we're doing. Why you taste so wrong? I don't know if this is a Haley song remix. I couldn't tell you. No, it doesn't look like it. So, this is your eccentricity vector. Don't worry about it. It's not a big deal. I will go over the derivation for this later, okay? But it's a little bit of a complex of a derivation, so I'm not going to go over it on stream right now. This is... What's it called? I have new homework. What's what called? I have new homework? Oh. This is on one of the Twitch libraries, Twitch playlists. Here, hold on a second. This is what I typically play on stream. It's called Orbit. Funny enough, it's called Orbit. Anyway, so this is your eccentricity vector right here, right? Which means to get eccentricity, I'm distracting you. Oh, it doesn't matter. It doesn't matter. If we just take the magnitude of the eccentricity vector, that's going to equal E. Okay? This is number 1, right? We've got inclination, and this is eccentricity. So, now we have two two elements that describe completely different things about our orbit, and they're not even dependent on time, right? So we now have number one is inclination, number two is eccentricity, okay? They define two completely different things, right? Our eccentricity defines how eccentric our orbit is, or how elliptical the orbit is compared to how circular it is. Whereas the inclination determines the angle in between your orbit and your reference plane, or your reference frame, right? That's the difference in between inclination and eccentricity. They're two completely different things. And I'm going to draw a nice little squiggly. Cool. But anyway, yeah, they're two completely different things, right? So we've got two. Let's move on, though. We can do better than two, right? How many do we need? That's right. We need 6. We need 6. Anyway, let's define a few things about our orbit. Doesn't Spotify change the UI when you're listening to Stranger Things playlists? I think that's how it happens. But we've got I and we've got E now, right? So before we move on, we need to define a few things about the orbit. All right, so this is the planet, right? And this is just a blank foci. Yeah, Kelly, I remember seeing that on the subreddit that happens. Anyway, let's define a few things about the orbit, right? So we've got this vector, and then we've got this long vector here, right? What do we typically call these two vectors? But we've also got this right here, so I'm just going to draw this out. Okay, so we've got this, and then we've got another thing down here. And then we've got this right here. Yeah, Kelly, it's a thing. Nope, definitely a thing. I saw it all over the subreddit. Alright, so this right here, I'll answer a few questions. This in orbits is defined as the radius of periapsis. This is defined as the radius of apoapsis. And this is defined as a value that we call p, okay? P is equal to the semi-latus rectum. Yeah, very funny. Semi-latus rectum, okay? Rectum as in, like, rectangle. No, it's my coffee, man. It's my coffee. My coffee machine turns off automatically after 2 hours. But that's what this P is. It's a semi-latus rectum. Rectum as in rectangle. And then we've got this value, right? That basically splits the ellipse into two. And we're going to call this A, right? A is equal to semi-major axis. Now, the cool thing about coming up with orbital elements is that not all of them are just specific to the three-dimensional shape, right? Or the three-dimensional direction. You also have a few parameters, like I'm sure you've seen semi-major axis as one of the 6, where A is actually just a property of the ellipse, rather than being a property of the direction and orientation of your orbit. And we can use A, right? So there's a few ways to do this. I'm going to start off, start off light. And let's come up with a different color. Let's do P in red. Okay, so what is P? P is a semi-latus rectum, and how do we calculate P? P is actually a really simple equation. P is equal to h, our angular momentum vector, the magnitude of that, squared over mu. And again, mu is equal to the gravitational constant multiplied by the mass of your body, otherwise known as the gravitational parameter. Whoa. Okay. Oh, get out of here, Carbonot. But it's equal to h squared over mu, okay? That's what your semi-lattice rectum is equal to. H squared over mu. And now we've got P, we can do a few other really cool things. What else do we know at this point, right? We also know, we know a few other things. He left? What? Let's see. We've got a few other things here. What do we already have, right? We already have. We have A. Well, no, we don't have A yet. Sorry. We have E and we have I. All right, let's try to find A. Oh, Carbonot. So we can actually solve all of these different things to get to A, right? So we've got P. P is actually also equal to this. P is also equal to P is equal to A times 1 minus E squared, okay? A few other equations that we have to our disposal. RP is equal to A 1 minus E. Radius of apoapsis is equal to your semi-major axis multiplied by 1 plus your eccentricity. A few other things that you have available to. But here's the thing. These are all dependent on A, right? We want to solve for A, not to fret. We have this awesome thing called algebra that we can use, so let's do that, right? So our semi-lattice rectum is also equal. Semi-lattice rectum, excuse me, is also equal to h squared over mu. All right. So that's equal to A times 1 minus E squared. Let's just solve for A. Okay. So we've got again, it's semi-major axis is equal to h squared over mu times 1 minus E squared. That's now on the bottom. All right, and we already have all the parameters we need for this. And that's just our semi-major axis, and we're gonna call that number 3. Okay. Wait, I missed a. Wait, what? Holy crap, Kelly! Kelly, cut that shit out! I keep telling you guys! I keep telling you guys! I'm not... I hate it. It's ridiculous, man. It's ridiculous. Guys, I do this for fun, alright? I'm not like a streamer. I don't do this. Subscribe to somebody else. Waste your money on somebody else. Don't do it on me. Come on. Come on, Kelly. Come on, Kelly. Is it even showing up? No, I have no idea why it's not showing up. Your subscription is not showing up. Like, it just did not register with the system for some reason. I have no idea why. Kelly, come on, man! Waste your money on somebody that does this for a living. Don't waste your money on me. I have money. I don't need money, okay? You're ridiculous. But yes, you get your rocket now. You get your rocket to use. I'm just... Again, thank you so much for the support, but it's not necessary, okay? But thank you. Yeah, I know, Demonata, I know. Just, you guys are awesome, and I love you for it, but this is a royalty-free. It's a royalty-free stream, okay? Alright, anyway, I'm gonna stop complaining about it. We've got our semi-major axis, number 3. Kelly, thank you. Thank you so much for the support, man. Seriously, thank you. We've got number 3 now, semi-major axis, right? So we now have we've got A, we've got E, and we've got I. Alright? Number, well, it's pretty crappy how I just did that. We have I, we have E, and we have A. Number 1, number 2, and number 3. Hey, Bougie, what's up, man? How's it going? Alright, so we've got A, we've got E, and we've got I. We've got 3 orbital elements so far. Let's define another orbital element, shall we? And this is when it starts getting a little bit weird, so just hold on to your horses. Okay. So let's draw our orbit one more time. Like this. Oh, that was pretty bad. I'm doing alright, man. We're trying to get through all 6 orbital elements by memory. I'm trying to see if I remember how to derive all 6 of them. Just kind of winging it, though. I got it so far, though. Now it's green. There you go, Kelly. Kelly, again, thank you so much for the subscription, but it's really not necessary. I mean, I'm not gonna complain, right? It's awesome. I love the fact that you guys are enjoying the content. So yeah. Okay, so we've got our orbit, right? And we've got where's the color that I want? Right here. We've got this thing, our angular momentum vector, and we've got our z-axis component, or our k-axis. What else do we have? We have inclination. We've got inclination already hammered out, which is this right here, right? We've got inclination. Okay. Okay. We've got inclination. We've got semi-major axis too. We've already got semi-major axis nailed down, right? This is our semi-major axis. Oh, that was bad. This is our semi-major axis right here. And I know this is probably really small to see, so don't worry about it. Yes, with impunity. So let's calculate another. Let's have another, please. I'll give you another. Don't worry. How P can be related to H? What, right here? Well, it's dependent on a few things, right? There you go, Kelly. So it's dependent on a few things, right? You can imagine it sort of like this. It's dependent on a few things. You've got that right. I'm gonna draw this, but I might delete it afterwards. So we've got a radius of periapsis, right? And let's just say your rocket is right here. Hey, thank you for the bit tips, Demonata. Jesus, I can't even say anything to you, Demonata, because you you guys are ridiculous. Thank you for the support. Whatever. I'm gonna stop complaining. Boom. I'm gonna be the better person. I'm gonna stop complaining about it. But cut that shit out. All right. So how can P really be related to H? Well, P is equal to a few things, right? P is equal to H squared over mu. Okay. So let's say that you're at radius of periapsis, right? And what is H? H is your position crossed with your velocity, right? That's what H is, right? All right, whatever, Demonata. Oh, get out of here, Kelly. I'm gonna wear it just because you said that. All right, Oyashiro. We've got radius and we've got velocity. We've got position and velocity. So it kind of makes sense, right? If you were to propagate out your orbit out to whatever point is directly perpendicular, this is going to be your P, right? Does that make sense to you, Oyashiro? This is going to be your P. Well, check this out, right? If we've got more angular momentum, that means a few things. That means either our position vector is larger, right? Because H is equal to R cross V. So as R goes up, H goes up too, right? And as V goes up, then H also goes up, right? So check this out. Oh, I've got Kelly isn't a fan of the NASA worm logo for some odd reason. I know, Callow, and I know, and that's what I'm gonna do. I'm gonna like do like at some point I'm going to do like a poll on stream or something to see like what you guys would care about or anything, like any the NASA worm logo shirt, any like group that you guys care about, for example. Anyway, I'm trying to answer this question and I keep getting sidetracked. So this is the P from the original orbit, right? So let's try increasing velocity. If we increase velocity, then what you can imagine then is that if you propagate your orbit outwards, right, you've got a lot more energy, so your orbit's probably going to look like this instead, because you're swinging it way far out. So this is P2, right? This is your new semilatus rectum. So do you see the dependence now? As H increases, your P will also increase. Now here's the other thing though. Mu is dependent on the mass, right? The center mass. So if you've got more mass here, if you've got like a lot more mass here, then even if you have like a larger angular momentum, your planet's going to pull you in tighter. So your P is going to go back down again, which makes sense. The heavier of a gravitational parameter you have, the less your semilatus rectum is going to be. So that's kind of that's the comparison why P has a dependence on H. So hopefully that helps a little bit. But that's what the dependency is, okay? And that's why there is a dependency. So anyway, let's take a look at what this is right here. Right? We've got a node. It's called the ascending node. I'm sure you guys have heard of the ascending node before, right? That's got its own components as well. And I know it's not really its component, but it lies in the IJ plane, right? IJ plane. Sounds good, Oyashiro. I'm glad to help, man. I'm always glad to help. So we've got this ascending node, right? And it's a hat, so it's going to be a unit vector is equal to ascending node. All right, and this ascending node is actually going to be relatively important to some other calculations, right? That we're going to have. So anyway, N is going to be our ascending node. How do we get to N? You may ask, and I may tell you. So here's how we get to N, right? What N is, it's actually really straightforward. What N is the following. N is just equal to angular momentum. Now you're going to cross. Well, actually, that's wrong. It's incorrect. What angular momentum, what your node is going to be K cross, the cross product of your angular momentum and your z-axis. And then obviously you're going to have to normalize this with respect to angular momentum to get it to be a unit vector. So if you cross K into H, right? If you can just imagine like crossing into H that direction, then the result is going to be a vector that's popping out the side like this. This vector, because of how H and K are defined, is going to be guaranteed to be in the IJ plane. And what this vector represents is when there's a crossover in between the lower half of the IJ plane and the upper half of the IJ plane. That's what that ascending node represents. It's the node that represents the change in between, okay, I'm below this plane and then I'm above this plane. This node represents when it happens, okay? Here's the really cool part. We can actually turn this into another orbital element if we're really, really careful about it. And the orbital element is going to be this angle right here, okay? Do you guys have any guess what this orbital element would be right here? And to help a little bit, I'll show again, like what I did with inclination, right? There's a few different orbits that you can come up with then, right? So you can imagine an orbit that's basically head on, right? You can imagine an orbit that's essentially head on. And let's draw the IJ plane like this, right? You can imagine that this value can also partake in a 0, right? Just like that. where if there's no change in this value, if that value is 0, then your orbit is essentially head on with the I-axis. Not quite, Bougie. We're not there quite yet, man. And then we've got another one, but Bougie, that's next up, man. Let's look at another orbit that maybe does have this value, whatever this value is. And now we've got an orbit that looks like this, right? We've got an orbit that looks like this instead. And now all of a sudden, this node vector is pointing out in this direction instead. So you can imagine we're kind of rotating our orbit around the z-axis, right? That's kind of what we're doing. So let me draw that. Z. Oh. So this is our k hat. This is our unit vector in the z direction. Right? So if we rotate around the k direction, we're kind of tilting our orbit a little bit. And now all of a sudden this has a value. This has a non-zero value, okay? And what we call this, it's typically denoted by an omega. So let me just draw omega here. Omega. And what this value is, it's omega. Omega, it actually has a relatively straightforward meaning. Like it makes sense what the name of it is. It's the right ascension. I think I butchered spelling there. Of the ascending node. Okay? It's the right ascension of the ascending node. You're taking your ascending node and you're seeing how much right ascension it has. That's literally what it is, right? You're taking your ascending node and you're seeing how swept along it is. Or for short, the RAN, right? RAN. Boom. So we've got a RAN now, right? So what exactly is this value then? This omega, this angle, that's what we're trying to calculate. Well, clearly it's the angle in between your, there you go, Bougie. Yeah, that's what right ascension of your orbit is. You're tilting your orbit around the z-axis. That's what you're doing with right ascension. That's what right ascension is. So, and again, it's just an angle, right? So we've got n hat. It's the angle between I and your ascending node. So, what that is then is the following. Omega is equal to cosine, inverse cosine of n dot I over the magnitude of... Oh, actually, you don't need that. Sorry. I'm not thinking, because those are both unit vectors, right? N dot I. Okay? That's all it is. Now, typically, right ascension is in between 0 and 360, okay? So we have to do a few checks here. It's really not that simple. But we need quadrant checks. We need what are called quadrant checks, alright? And the reason we do quadrant checks is because trigonometric functions like this aren't always guaranteed to return in between 0 and 360. Yeah, there you go, Bougie. That's exactly what right ascension is. So, we're going to do this. Omega equals the following, right? And here's what it's going to equal. How do I want to do this? Yes. It's going to equal the inverse cosine of your n hat vector multiplied by your ascending node vector multiplied by the x-axis if the y component is greater than or equal to 0, okay? And I'll show you what this represents in a second on the orbit. Is greater than or equal to 0. Else, it's going to equal 360 degrees minus cosine -1 of n hat multiplied by I hat. Your ascending node vector multiplied by your x-axis. If your x-axis unit vector. If nj is less than 0. Okay? And this is number 4. Okay? So, here's the thing, right? This obviously has a y component at some point, right? It's got a y component that's in this direction, right here. This is nj, right? In this case, nj, the component of n in the j direction is equal to 0. Maybe I should draw the fact that this is j hat. This is the y-axis right here. So here's the thing. This angle is high off. So if you switch your orbit, like in a retrograde orbit, right ascension isn't necessarily the value that changes. Right ascension is always defined as going from below to above the xy plane. Booty, what changes then, if you have a retrograde orbit, then this is no longer your h value, right? Here, I'll show you. Let me just show you real quick the difference between prograde and retrograde orbit. Right, so if you've got 2 orbits that you're looking at, one is prograde and one is retrograde. Wow, nice orbit. One is okay. So color. One is going in this direction, and then the other one is going in this direction. Okay, what changes? Yeah, so exactly, it's on the other side, but you don't need to worry about that calculation, and I'll show you why. You don't need to worry about offsetting it or anything like that. And the reason because of that is, in this case, your angular momentum is defined as this, but in this case, your angular momentum is defined as this. Okay? Now, the difference that comes into play with prograde and retrograde is not necessarily right ascension, because again, right ascension is going to be calculated as right ascension because it's your ascending node that you're looking at, right? The difference is your inclination. That's what's going to change. The difference is your inclination. Right here, your inclination is right, that parameter, but down here, your inclination is this parameter instead. So there's really not, such a thing as a retrograde orbit, right? There's no such thing as a retrograde orbit. A retrograde orbit is, when you're looking at this, it's just typically defined as an inclination higher than 90 degrees, right? So if you've got like a flat orbit, so here's another way of looking at it. If you've got 2 flat orbits like this, and if you've got one orbit that starts right here and goes this direction, and one orbit that starts right here and goes this direction, depending on what your reference frame is, if this is your z-axis right here, right there, kind of coming out of the screen, then the difference is that this is inclination is equal to 0 degrees, and this is inclination is equal to 180 degrees. Okay, that's the difference there. As you probably have noticed, there are exceptions. I'm not going to go too far into it, but yes, when you have a 0 or 180 degree inclination orbit, your right ascension is undefined. Not going to get too far into that. There are some discontinuities in this model of orbital parameters. A neat thing to notice, though, is that this is not the only set of orbital parameters. Well, that looks like crap now. Yeah, it's really not swapping anything, right? It's just it's a different yeah, and I completely forgot about this. It's just a different orbit. And obviously, if you've got a different orbit, then something does change. But the thing that changes is not right ascension. The thing that changes is your inclination. That's what's different in between a retrograde orbit and a prograde orbit. I'm gonna just throw everything on the side there. Okay, so now we've got 4, right? So now we have we started with inclination, then we calculated eccentricity, then we calculated semi-major axis, then we calculated right ascension of the ascending node. So we've got 1, we've got 2, We've got 3, and then we've got 4. Holy crap. We've got 4 out of 6. Alright, we're getting there. We are getting there. Back to prograde. Oh, dude, it doesn't matter. Again, the whole point is, like, you guys can ask me questions. It doesn't matter. Anyway, we've got 4 out of 6. Making progress. So, for our 5th one, we're going to go like this. Now we need to define how the orbit is oriented in plane. So we've got our K, unit vector. We've got I down here, our unit vector. And we've got J, our unit vector. Okay? Let's say that we've got somewhat of an eccentric orbit that looks like this, right? Whoa, come on now. This is our periapsis point. It shoots down, right? But then it goes really far on this side. And then it comes back like this. Okay, so this is our orbit. We've got an ascending node right here, right? So this is our n vector. We've got a few other things that we know right off the bat. Where's the right color here? Never to the right color. We've got angular momentum coming off the page here, which means inclination is right there. And again, this is right ascension of the ascending node, so we've got omega. So we've got a few things right here. This is actually a vector. So what this is, again, we already went over to this. This vector is actually the eccentricity vector. Eccentricity is a vector. It's not just a magnitude value. So we've got this, right? That points in the direction of your radius of periapsis. That's how the eccentricity vector is defined. Well, check this out. Obviously, there's some rotation in between where the eccentricity vector or where your periapsis vector is within the plane of your orbit, right? Because you can imagine you can also have the same exact orbit, but you're shifting it in this direction. So your eccentricity vector, or you're rotating it in this direction along the angular momentum vector, where your eccentricity vector lines up perfectly with your ascending node, right? You can have a multitude of different orbits like that. But in this case, you're looking at an orbit that does have a rotation along your angular momentum vector that's slightly offset, right? Which introduces this angle right here, okay? And we're going to call this angle little omega. Little omega, little tiny omega, like that. That's another angle that we need to solve for now. Who can tell me what the name of this angle is? The rotation in plane, right? We did the rotation along the z-axis, which was right ascension of the ascending node, but now we're rotating it in plane. Bougie, you better know, because you just answered this yourself. You answered it last time. You better know the answer to this, Bougie. What is that angle called? Yeah, Bougie's got it. Bougie's got it. Hold on one second. It's called the argument of periapsis. Fred, that's not his name, no. This omega, little omega, is called argument of periapsis. Argument of periapsis. Okay, and it's in plane rotation. Orbit rotation. Wow, English? It's in plane orbit rotation. Okay, that's what argument of periapsis is defined to be. And it's pretty obvious, right? It's just the angle in between the ascending node and your eccentricity vector. Pretty straightforward, alright? It's the one that looks like a butt. Yep, that's argument of periapsis. Is tied to precession? No. No, precession is completely different. I'm assuming a two-body model. I'm assuming no precession, no nutation, or anything like that. you're thinking of, yeah. So let me draw this out. Not to be confused with, with the vector omega, which is angular velocity, right? That's what this vector is defined as. And the angular velocity is tied to attitude rates, precession, etc. All right, so this is angular velocity. Yes, that is tied to precession if you're looking at attitude dynamics and attitude body dynamics, rigid body dynamics, excuse me. But we're not going to get into rigid body dynamics for a long time. I don't even think we'll get there, to be honest. I'm sure that I'm going to cut this series loose before I get to precession and nutation in attitude dynamics. But yeah, this is the value that's tied to attitude dynamics, right? It's a little bit different. But I'm looking at this, which is the same letter, but it's defined as something completely different. It's the argument of periapsis. And as you can imagine, we need to do quadrant checks, right? So omega is equal to the following. It's equal to the inverse cosine of your eccentricity vector dotted with your ascending node vector over your magnitude of eccentricity if EZ is greater than or equal to 0. Wasn't that easy? Yeah, it was easy. Or it's equal to 360 degrees minus the inverse cosine of your eccentricity vector dotted with your ascending node over the magnitude of your eccentricity vector if EZ is less than 0. Okay? So what this represents is this right here, right? So if your eccentricity vector has a... Yeah, I'm not going to be able to fit that in there. Well, actually, I can kind of draw it off to the side. So you can kind of imagine this component right here is EZ.